Can you all hear me all right? Cool, thanks. How's it going? Yeah, that's about right. Right on. I almost forgot to eat lunch before teaching today, so. Everyone looking forward to the weekend already? Because I know I am. I have a lot of my own stuff that's due on Friday, so I'm ready for that to be over. No, there was not a new vocab or quick. So there was a quick quiz. Did it not show up for you? So there. Okay. Let me check that real quick because I'm pretty sure I posted the quick quiz for today. Let me double check. Yeah, no, there's a quick quiz that was due today. Although I realize I didn't set a due date on it, but it is there. So I will set it for 3:15 today since it has been posted since yesterday, or not since yesterday, since Monday. But I realized I didn't set a due date on it. So yeah, most people did it already. But if you didn't, go ahead. Let me go back to the PowerPoint now. Okay, do you still see PowerPoint? Oops. Yeah, okay, cool. Yeah, so yeah. So the reason it wasn't in notifications is because I did forget to say when it was due. But again, there's always going to be a quick quiz. So when in doubt, just check. But I did go ahead and do it now, I guess. I changed the due date to 3:15. I guess I can change it to 3:30 after class since we're in class. But let's get started. I'll go back to that and update it right after. So there will be yet another quick quiz posted immediately after class today, and I will double check to say that it has an actual due date on it. There will also be a new vocabulary for next time. So today we're going to finish up with metamorphic rocks, and then on Monday we're going to talk about geologic deformation. And then next Wednesday, we do not have class. So even though Wednesday is technically not a holiday yet, it would just be crappy and mean to have class the day before Thanksgiving. So we're not going to have class the day before Thanksgiving. So next week, we just have the one lecture on Monday. And I also, okay, can anyone else, can everyone else hear me? Okay. Yeah, so Jasmine, I think it's just you. I would try logging out and logging back in. Yeah, so next week, again, there will be class on Monday, and then I'm not going to have office hours next Tuesday, the Tuesday before Thanksgiving, just because, again, we really should get that whole week off, I think, but we don't. And so I will, in exchange for that, have an extra sort of study review session before our final at a date to be announced. So I'll sort of poll you all on the best date for that probably next week. So again, next week we just have one thing, and then the week after Thanksgiving, we have our 2 lectures on earthquakes, and then it's already the end of the semester. So our last regular test is December 7th. It'll be like all the others, where we review in here for 25 minutes, and then you have 30 or 45 minutes to do the test. And then our final is the following Monday. It is December 14th, and it is from 3 to 5. So that is the time they gave us. So please mark that in your calendar, that it is from 3 to 5 and not 2 to 4, because it will only be available for that time. And I will remind you, but it'll only be available for that time. And the final will be open notes, open book, open Canvas, etc. But not, the date is December 14th. And all of this is on Canvas as well and in the syllabus. So if you forget, it's in there. But yeah, it's that's going to be open everything except talking to other people. So you can consult the internet, but you can't make a post on a forum. You can't ask another person, whether it's in person or email or text or whatever. But otherwise, you can use all your notes. So I would definitely just, thinking advance to December 14th, make sure your notes are really well organized so you can find everything really well. But yeah, any questions about anything logistical before we go on? Cool, then I am gonna go on. Whoops, not like that. Okay, okay, so the final is everything. So the final is going to, it can be anything we talked about in this class is game. So I will have a review session where just like with the others, I'll have a little box open that you can submit the stuff you want me to review. But the review session will be at a, it's not required. It'll be at a time probably at when my normal office hours would be, but we'll see. And I can go over people's specific questions, but literally everything is fair game. And the final is going to be stuff like, it's not going to be like recalling facts. It's not going to be like, is sandstone igneous, sedimentary, or metamorphic? It's not going to be stuff like that. It's going to be stuff that's interpretive. Like there's going to be things like, here's a rock, its characteristics are this, this, and this. Tell me these things about it. Stuff like that. So it's going to be stuff that like there isn't, it's about using interpretation and about combining the facts that you've learned throughout the semester to understanding and interpreting things, to telling geologic stories. But basically anything is fair game. So just go over those study sheets and think about what you're most confused about, and let me know what you want to go back over when it's time for that. But the regular 4th test is just going to be metamorphic rocks, deformation, and earthquakes. So anything else before we go on? All right, so let's come on. So this slide that's up now is the slide that we ended with last time. So last time we talked about just the definition of metamorphic rocks and the general structural groups of foliated, where it's organized in a fabric of minerals that may or may not be layered based on content. And we talked about ways metamorphism occurs, like different metamorphic processes and how they're controlled by temperature or pressure. And yeah, I agree, Elaine. It is really a shame. I'm really glad you're enjoying it anyway. There are other geology classes. I guess before I go on, if you are interested in, I guess it's still not going to be face-to-face, but if you want more California specific stuff, because a lot of people on their poll that I did at the end of the second test said they wished we'd talk more about California specifically. There's kind of not a lot of time to do that in this class, but Geology 344 is a class I'm teaching in the spring. It will unfortunately be all online, but it's more California specific. So I'll put that in the chat box, but then we are gonna go on and finish our metamorphic rock stuff. And if you want to talk more about other stuff, as always, I can hang around a little at the end. But anyway, yeah, so we talked about metamorphic processes, about how rocks change, about how the minerals in them either change structure or change entire chemistry or whatever, based on temperature and pressure. And we talked about how very often the protolith, which is the rock that was there before metamorphism, often that has less impact on the resulting metamorphic rock than you'd think. So sometimes the resulting rock looks a lot like the protolith, and sometimes it looks nothing like the protolith. So I will never give you a question that's like, here's a metamorphic rock, tell me what the protolith was. I will not do that, because that's mean. But I might, but because there's so much variation and because some of the changes can be very extreme, it's harder to categorize metamorphic rocks than igneous or sedimentary. And so the way we do it is actually based on temperature and pressure. And so the intensity of metamorphism, the amount that a rock has changed, is called its metamorphic grade. And so for the most part, metamorphic grade is it's more influenced by temperature than by pressure. And so in places like contact metamorphism, which is just something hot touching another rock and changing its structure, that can happen at very shallow depths. And so low grade is lower temperature, intermediate grade is intermediate temperature, and high grade is high temperature. But when you're talking about situations where there's higher pressure, like in a mountain belt where two continents are crashing into each other, because the pressure is so high, that actually means that it takes higher temperatures for things to work. Just like if you remember when we were talking about the structure of the Earth, or when we were talking about why the mantle isn't molten, it's because the pressure keeps that from happening despite the high temperature. And so in this case, even though there's no melting involved, the higher pressure also means that higher temperatures are required to make things work under that pressure. So low-grade metamorphism at high pressure is still lower temperature, but it goes to a higher temperature than it would at low pressure, and so on and so on. So, and then worth noting, subduction zones are a special case. We call that blue schist grade, which is its own thing that we'll talk more about later. But that's because subduction zones have very high pressure and very low temperature. So you get some really unique situations in there. But does this general thing make sense? So if you notice, this is the same parameter space as that liquidus solidus chart. You have temperature along the top and pressure or depth along the sides. So if I were to give you a question like, you have a rock that is this temperature, at this temperature and at this pressure, what grade of metamorphism is it? Would you understand how to use this chart? Or do you want me to do one? I will do one. Let me get up my pen. Okay, so let's say that you had, and once again, I'm gonna hopefully draw straight lines. Hopefully your lines will be straighter. Let's say you had something that was at, let's say you're at 500 degrees Celsius. So you wanna go over to that line. Actually, no matter what for 500, it's gonna be one of them. Let's say you are at, 450 degrees Celsius. So that's about here. So you're going to draw a line down as straight as you can. That one was pretty good. And then say you have something that's at a pressure of 5 kilobar. So you would go over here. So here's 4, here's 6. Once again, draw as straight of a line as you can. And then where that intersects, actually, that was a really bad one because that's right on the border. But this is more yellow than orange. Okay, so like where if that is at, if that's at this temperature and this pressure, is this low, intermediate, or high grade?
Intermediate. No.
Yeah, so this one I realized I chose a value that was at was really close to the border, but let's say that the border is here.
My bad.
So it's low. I promise that I will make it more clear on the test. I was just pulling numbers out of thin air right now. But now let's say that it was at that temperature, but at a pressure of half a kilobar. That was not a straight line at all. Pretend. Okay, so that one over here would be an intermediate grade because it's in the orange. I will make the colors and lines clearer in what I give you. But do you see how that changes? How like if the boundary is here for for contact metamorphism and here for mountain belt metamorphism. Or now let's say I gave you a thing where I said, okay, we're still at 5 kilobars, but we're only at a temperature of 200 degrees Celsius. Where do you think we would be? What kind of metamorphism are we talking about there? See if you can guess it before I draw it. So at this 500 or 5 kilobars, so along this line, but at 200 degrees Celsius. So so it's in blue schist. Yeah. So when in doubt, like definitely hold up rulers, draw it. Like, make sure you you can like hold stuff up to the screen, mark it, trace it, do things, draw it yourself. Definitely, it's easier to draw these than to eyeball them. Because obviously I was trying to eyeball one that was more obvious over here, and then it ended up being less obvious. But does this general idea make sense? Yeah, at 5 kilobars. Yeah. And also, it'll be written down for you anytime. And by the way, you will have practice problems up about this and the next 2 slides later today, like after lecture as well. I will not give you one that is in the area that's not marked. But basically, what that means is those are kind of not conditions that happen, just because generally, just you don't really have situations that are in this middle ground. But I won't give you ones that are in the middle. Are we good on this slide before I go on to the next one? Okay, so even though these are temperature and pressure conditions and we know things about them, once you find that rock on the surface of the Earth, it's on the surface of the Earth. It's at low pressure and low temperature. You're not going to be able to tell these things necessarily. Sometimes you can tell from the structure of the rock, but the best way to tell what the grade of metamorphism is when you actually find a rock is to look for what minerals are in it. So even though the protolith doesn't necessarily matter that much because metamorphism completely can break apart the bonds and reassemble them into different minerals. The specific minerals that form only occur in certain conditions. And so by finding those minerals, like if you find certain combinations of things, you can tell what metamorphic grade it is. And so we call those index minerals. There are dozens and dozens, if not hundreds, of different minerals that can form in metamorphic conditions, but index minerals are really, really common ones that only form in these certain conditions. And so if you can go, okay, these things are in a rock together, it must be this grade. So this is another chart. So this is a chart of index minerals for protolith, low, intermediate, and high grade. And it separates basalt from a shale, because sometimes an igneous rock is going to have different minerals in it than a metamorphic, than a sedimentary rock. And so you might end up with some different stuff. If I give you a question about this, I will always specify if you're talking about an igneous rock or a sedimentary rock as the protolith. I won't make you either that, or I'll give you minerals where you'll be able to tell. But the way this works is like, okay, so let's say you find, so these are all names of minerals. We didn't talk much about, we talked about amphibole, we talked about quartz and feldspar, and a lot of these guys. Don't worry about memorizing these mineral names. You don't need to know the structure of these that aren't the ones we already talked about. But like, let's say, for example, that you found amphibole and garnet together in a rock, in a metamorphic rock. So if you found amphibole and garnet, would you be able to tell which grade it is? So what grade is it then?
Would it be intermediate grade?
So it could be.
Yes, that's my answer.
But can you tell if it's only going to be intermediate? Because this line for amphibole goes all the way out here.
Oh, I didn't see that.
So definitely look at these charts really carefully. Yeah. So if you just found amphibole and garnet, you wouldn't be able to tell if it was intermediate or high. But if you also found, and even if you actually also found pyroxene, which is this one down here, that overlap is here. So you still wouldn't necessarily be able to tell if you only found those three. Whoops. But let's say you also found epidote. Well, actually you wouldn't find, actually, never mind, no. You wouldn't, if you found epidote, you would not also find pyroxene. So even though pyroxene goes over here, it doesn't overlap with any of these other things. So I guess it could be intermediate, but you wouldn't be able to tell if it was intermediate or high. But if you didn't find pyroxene and you did find epidote, then it has to be intermediate. So does that make sense? Yeah. So in this case, like amphibole, garnet, and pyroxene tells you it's either intermediate or high, and you can't necessarily tell which. But if you find garnet, amphibole, and epidote, you know you're dealing with intermediate. Or let's try another one. Let's go down here. Let's say you found some feldspar. Does that give you much information? Going down to the bottom one.
No, it doesn't.
Yeah, so feldspar could be freaking anything. Feldspar and quartz are the two most common minerals on the Earth's crust. So now let's say you also found muscovite. Does that help you? So here's muscovite. So it helps a little. So by finding muscovite, it rules out high grade metamorphism. So you know it's either low grade or intermediate grade. So let's say you found, if you found biotite also, would it help? Yeah. So biotite would not help because it's in all three of these. It goes from here to here. Kind of useless for this. But if you found garnet, would it help? So was that no to garnet? Okay, so garnet does overlap the quartz and the feldspar and the muscovite. And so if we know that muscovite doesn't exist at high grade, whoops, and garnet doesn't exist at low grade, If you find all three of those together, what must it mean?
Mom, I said yes to Garnet helping.
Oh, okay, yeah, sorry.
No,
So
it's
yeah,
okay.
so yeah, Garnet would narrow it down to being intermediate. Or if you found chlorite instead, it would narrow it down to being low grade. Yeah, so do you understand how this works? So this is the kind of thing where there'll be practice problems about this too, where if you, I might give you some minerals and say, can you tell what grade this is? And things like that, or things like what mineral would you need to find to narrow it down? Things like that. So any questions about this before I go on? And I'll try to get a nicer looking print of this on the test. And again, this chart, the previous chart, and the next chart, I will give you all of them. You do not have to memorize these. So yeah, we talked about grade, and we talked about the index minerals that you can use to find those grades. But as it turns out, you can have different grades of metamorphism in different settings. So it's not like low grade only occurs in one place, or high grade only occurs in one place. Like we already established that with this chart, because there's a different curve for in a mountain than for in contact, than for in a subduction zone. So that combination of what minerals you find and what grade they are actually comes to a third, more complicated kind of classification of metamorphic rocks called metamorphic facies. And so this is another chart of temperature along the top versus pressure or depth on the side. But these are kind of combinations of both structural and chemical classes of rocks. So this basically says this is the category of rock you're going to get under these conditions. And so sometimes you can have low or high grade ones of a certain category. Sometimes a category is inherently high grade. Sometimes it changes. So in this case, diagenesis is just a fancy word for what happens with sedimentary rocks. So this line below this curve is not metamorphic. But all of these other categories over here are categories of metamorphic rocks. So like you can talk about, low pressure metamorphic rocks are going to be hornfells, which we talked about last time. We'll talk more about today. So this is a situation where you have high heat and low pressure, and that category is going to be hornfells. And those are contact metamorphism rocks. We'll talk more about contact metamorphism in a few slides. The opposite is where you have very high pressure and very low temperature is your blue schist subduction zone rocks. And so hornfells, kind of the chemistry actually doesn't matter. It's kind of the kitchen sink. Blue schist has very specific minerals in it. Zeolites are a very specific group of minerals that form under low pressure and low temperature. But then kind of in the middle, like your mountain belt stuff, you can get different categories, your green schists, amphibolites, granulites, and eclogites. Don't need to worry about memorizing these names either, because I'm going to give you this chart. But basically, these each have different categories, kind of depending on what has happened to both the minerals and the structures of the rocks. So green schist is going to have structural change and mineral change, but the minerals will change to certain things and the structures will change to certain things. Whereas in granulite, those will change to different things, even though it starts with the same material. Does that make sense? So eclogites, you're basically almost in the mantle already. Yeah, so I can say that again. So basically this is a what category of rocks form at different conditions. So if metamorphic grade is just describing the amount of change and the index minerals can help you tell, metamorphic facies are actually categories of rock based on chemistry and structure that occur at these different things. So it's like grade, but with more structure and chemistry. It's not just like how much did it change, but how did it change? So So like you have your low pressure, your high temperature, low pressure hornfels, your low temperature, high pressure blue schist, and then kind of in the middle, green schist, amphibolite, and granulite are all increasingly high pressure and temperature, but they all have both structural and chemical changes, but the nature of those changes is different compared on which conditions you're in. So in all of these, minerals are going to turn into different minerals and the structure of the rock is going to change. But the specific details of those minerals and the specific details of the resulting structure is going to change depending on how hot and how much pressure. So does that answer your question? So another thing to notice on this chart is if you go down here, a lot of these little things indicate there are numbered things indicating what place in plate tectonics you're going to find this stuff. So like contact metamorphism is, again, where some hot rock touches rock that's not hot and just bakes it. So that tends to happen. That's where you get hornfels. We already talked about, so an accretionary prism is, we'll talk more about in a second. It's basically when you have a subduction zone and one plate is going under the other and a bunch of stuff gets stuck in there. That's where most of the blue schist metamorphism happens, is in that wedge that's kind of stuck between the plates. So that's basically a subduction zone. You can get green schist just in a continent existing, because if you get deep enough into the thick continental crust, there's still enough heat and pressure to cause some fairly low to moderate grade metamorphism. Then in a collision, in a continental collision, you're going to get pretty high grade stuff because you're crashing things into each other. There's a whole lot of pressure and a whole lot of heat. And then in a volcanic arc, there's a lot more heat because there's molten rock around to add to the situation. So you get something else altogether. So all of these are structural and chemical changes. Actually, they all are, but it just depends on what stuff is in which condition. So does that help? So this is the kind of thing where I might ask you, again, I might give you this chart, although without the like numbered, I might take the numbers 1 through 5 off it. And I might give you this chart and be like, let's say you're at a pressure of 8 kilobars and a temperature of 500 degrees Celsius. What metamorphic fascies are you going to get? And that works, and this would work exactly the same way. So if I were going to say 8 kilobars, it's a really bad line. 8 kilobars. And what did I say? Did I say 500? I'm going to say 450. 450. You would do the exact same thing and go, okay, where they intersect, that's green schist. So this chart works exactly the same way as the other. It's just telling you different things. So are we good on that? And there will be some stuff using this one in those practice problems as well. So you will get ample practice. Could I do 708? Sure. So 8 kilobars and 700 degrees. Okay. So we're going to leave our 8 kilobars line. And so in this case, you're on the border here. So this puts you kind of between amphibolite and granulite. And that's sort of the reason you have that kind of wiggle room is a lot of it will depend on the very specific details of the situation, on what minerals are there, on how much of things are there. I will not give you a question where it is in the middle. So don't worry about that. Does that help? Are we ready to go on? All right, let's keep going. No worries. No, do not apologize. I build in time to answer questions. So we're doing fine. I'm just checking my watch to make sure I'm where I think I am, and we're good. But yeah, so all three of these charts are things, there will be questions about them on homework, and there will be questions about them on the test. Know how to use them. Don't worry about memorizing them. But as we see, there's a whole lot of different conditions that rocks can turn into totally different things, regardless of their starting minerals. Like even if you put the exact same protolith into each of these different conditions, you would end up with a very different metamorphic rock. And as this starts to hint at down here, those conditions tend to occur in very specific places or settings on Earth. And so what we're going to do actually for the rest of today is just go through the different environments in which metamorphism occurs and talk about some of the specific kinds of rocks that form there. So are we ready to go? So yeah, metamorphism requires extreme conditions. It requires high pressure and high heat. Although not enough heat to melt things, because if it melts it completely, it's not metamorphic anymore. But there's a lot of different settings. And so we're just going to go through them. Hopefully these will all sound familiar from your vocab homework. So the first one we're going to talk about is the simplest one, and it's called burial metamorphism, which is exactly what it sounds like. It's just you get a lot of pressure from burying rocks under more and more stuff. And so if you think that sounds like sedimentary rocks, you're very much correct. In this case, burial metamorphism is basically just an extension of the sedimentary process. So if you remember, for sedimentary lithification, you have cementation, where cement, a chemical cement, kind of sticks all the clasts together, and then compaction that turns it into a rock. So in this case, the compaction process just gets more and more and more intense, such that you start to get some recrystallization of the cement. And so it's usually the materials in the cement that metamorphose and that the clasts themselves do not, but that's still enough to count as a metamorphic rock. And so it's really low heat, and in the grand scheme of things, this is actually still pretty low pressure. Even though it's entirely pressure-based, it's nothing like super deep in the ground. And so this is still a low-grade metamorphic situation. But yeah, does this general idea of just eventually when you put enough stuff on it, it starts to change structure, does that make sense? I mean, we already had pressure help turn sediment into sedimentary rocks. This is just turning sedimentary rocks into metamorphic rocks. And so the stuff that you're going to find in a burial metamorphism setting looks a whole lot like the rocks that were sedimentary. These almost always have sedimentary protoliths. Occasionally, you might have some igneous rock or metamorphic rock that gets buried by sediment and turns into something else. But in general, because this is a direct extension of lithification, of sedimentary lithification, or diagenesis is another word for that. These things almost always have sedimentary protoliths, and they almost always look like what they did before. It's a very subtle recrystallization. And a lot of these things have really, really basic names, like metasandstone. Starts as regular sandstone, but then it metamorphoses. So if you were to look at this and compare this to some regular sandstone, just from the naked eye, it would be hard to tell. But if you looked at it under a microscope, for example, the cement, rather than just being solidified mud or whatever, would actually show signs of recrystallization of those crystals breaking down and then turning into larger ones. Similarly, like metaconglomerate, starts like regular conglomerate, but then as it gets squeezed, especially in the cement and especially around the edges of the larger clasts, you get, again, some breakdown and recrystallization. And so the places that you would most likely find metamorphism in this would be like in these areas. If you were to put like this stuff around or under a microscope, you would see that this has recrystallized and changed structure, even though the rest of the rock is probably pretty close to what it was like before metamorphism. So a lot of times they have names like this. Sometimes they don't. Like slate starts as shale. And it's just shale that gets squished enough that it starts to foliate, but it still just comes from an increasing accumulation of sediment. But yeah, this is just, you pile it up and it gets crushed until it turns into something else. So any questions about that one? The others are more exciting. This is like probably the least exciting one. Yeah, so let's go on. So context metamorphism, I've already used this phrase a lot. And now we're actually going to talk about how it works. And so it's another one that, like, if you think about it, it's exactly what it sounds like. Really, all of these are exactly what they sound like. It's just that some of them have more technical terms for them. So context metamorphism just means that you've got an igneous intrusion and it's hot and it's just baking the rock around it. Just like how when you make some dough and you bake it into bread, even though it's the same stuff in there, the structure of that stuff changes. It's the same idea. It's baking the surrounding rocks and turning them into something else. And so if you remember our diagram of igneous intrusions from a couple months ago, whenever that was, like you would get that like around here, like along this dike or along the volcanic pipe. You get that at the edges where rock that's not associated with volcanism touches the hot rock. And so this is inherently a high heat situation. You're dealing with magma, but it's usually pretty low pressure. And the grade of the metamorphism just depends on how hot it is. So if you're talking about a rhyolitic magma, a felsic magma, which melts and solidifies at lower temperatures, then you're going to end up with lower grade metamorphism than if you're talking about a basaltic or mafic magma that is very high temperature. So I showed you this picture also when we talked about igneous rocks and about intrusions. And so right here is the intrusion. But here you can see these areas that are sort of white. You can see the intrusion is black and most of this rock is gray. But can you see these bands of lighter colored rock that are sort of following the path of the intrusion? So those are bands of contact metamorphism. And so in general, the grade of that contact metamorphism will be the highest right next to the molten rock and the lowest as it goes away. So it's kind of a gradient as you get further and further away from the heat source. So does this general concept make sense? So the force at work here is, again, another recrystallization force. Sometimes there's a little bit of neocrystallization, but for the most part, it's just recrystallization where the heat is breaking bonds and then they're coming back together into larger crystals of the same thing. So the rocks that you're going to get in contact metamorphism are called hornfels. And again, don't be confused by fels in this word. It has nothing to do with mafic or felsic. It's just from the German word for rock or boulder. So this one is a German word origin. Has nothing to do with feldspar. You can have a very feldspar rich one. You can have one that doesn't have any feldspar in it. Hornfels is just what happens when you have contact metamorphism. And so this rock can look like many, many things. I'm never going to be like, here's a rock, is it hornfels? Because it looks like so many different things. All of these very different looking rocks, very light gray, sort of dark dull gray, shiny black, this mustard color, this stripy thing. These are all hornfels. But worth noting that hornfels is not a foliated metamorphic rock. These stripes are because this rock had stripes before it had metamorphism. So this was a sedimentary protolith that when it had contact metamorphism and turned into hornfels, it kept those stripes. So are there, but yeah, hornfels is just, again, it can be the kitchen sink. That's why it's a category. It's defined by its structure, not by its chemistry. So if you remember going back over here, it's this whole category, this whole facies is hornfels. So any questions about contact metamorphism? Great igneous bake-off, I guess. Anyway, moving on. So now we're going to get more exciting. So for the most part, burial metamorphism is a very slow, steady process. And contact metamorphism, I mean, it involves molten rock, which is kind of exciting, but it still happens over time. But dynamic metamorphism is another one where it's exactly where it sounds like. Dynamic refers to fast, refers to motion. It is metamorphism that occurs because things are moving quickly. And so in this case, it specifically occurs to when rocks are sliding past each other, when you have the frictional sliding of large blocks of rock past each other, usually very quickly. And so this tends to happen in earthquakes, sometimes in landslides and other mass movements, sometimes near glaciers. But for the most part, this is very much an earthquake-related process. And so this is also why we're going to be talking about earthquakes as part of our metamorphic rocks unit. So basically, you get this in what's called a shear zone. So we'll talk more about shear on Monday. But shear is basically moving things side by side past each other. And so in this case, when you do that very rapidly, it heats up very quickly due to friction. And so even though it's only for a few moments, that heat is enough, that frictional heat is enough to make things very plastic and deformable and break some bonds, and also just allow both the heat and then the dragging of one rock past another to align minerals in the direction of the shear. And so in general, you might see, these are usually very narrow. You usually get these in very, very narrow zones right along where it's moving. Is that movement similar to tectonic plates? Yeah, it's related directly to the movement of tectonic plates. So the tectonic plate movements, as we'll talk about after Thanksgiving, are what drive earthquakes. So you wouldn't get this without tectonic plate motion. But even though we're talking about sometimes entire plates moving past other plates, the zone of dynamic metamorphism might only be an inch or less wide, depending on how clear cut that surface is. And so in the shear zone like that, you're going to see a lot of mineral grains that have been aligned with the direction of motion and stretched out because they got really hot. And so this is, if you remember when we talked about glacial striation, about how a glacier moving along something can drag grooves into the rock, this is not unlike that. But rather than it making grooves, it's just the dragging is what's pulling and stretching these things out in the direction of motion. So does that make sense? And this often happens really instantaneously, like in a matter of seconds. So it's not, so even though it might get super, super hot, it doesn't last long enough to melt most of the time. So yeah, this is a very high heat situation. It's moderate to high pressure, depending on how deep down in the earth it's happening, how deep down in the crust it's happening. This is all still in the crust. And it usually ends up in some pretty high grade rocks just because it's high heat and high pressure, even though it only lasts for a very short amount of time before it cools back down and goes back to no pressure. So the rocks that you get in these situations are they're called myelinites. And so that's where, again, that heat and rapid motion align and stretch the minerals. So this one on the left is a thicker myelinite. And you can see, can you see how there's a lot of bands of things? So you can, that is a form of foliation, but you can also see that they're really, really parallel to each other because that was the direction of motion. But you can also see, do you see this, this larger, this is probably a garnet, this red thing? I mean, do you see how it kind of has, it looks a little bit like this is moving this way around it, and this is moving this way around it? Do you kind of see those flow lines around it? So basically that, because garnet is a high-grade metamorphic mineral, it is harder for it to get stretched and modified, so it kind of gets pulled along. And you can often see results of, like, signs of a rock kind of tumbling or rolling around as it gets dragged in myelinite. So that's that one on the left. The one on the right is just an example of a really narrow band of myelinite in, so this is also definitely a metamorphic rock that it's in. But can you see how this band, like how outside of here, all of these minerals are just kind of in whatever orientation they want to be in. And in here, everything is aligned this way. Do you all see that? So that's really saying that this very narrow zone is where all of the action was happening. You can see a little bit of alignment over here, but really it can sometimes be very, very narrow space that a huge amount of force and heat are happening on, which is why you can get such dramatic metamorphism. And you can sometimes also get something called pseudotacholite, which is basically it's a kind of metamorphic glass. And it's where just the very surface of the rock, right where this, the things are sliding past each other, does get hot enough to melt. But then it cools so quickly, and it's only the surface of the clasts. It's not like the entire rock that's melting. It's just the surface that melts and then immediately turns into a glass. So you can get pseudotacholite on myelinite. And it doesn't count as igneous because it's not everything melting. It's just that slipping surface that's melting. And so this is actually really rare to find because it's such a thin layer of glass. I mean, partly because this tends to happen pretty deep in the earth, but it's also such a thin layer, or pretty deep in the crust rather. But it's such a thin layer that it easily degrades when it gets to the surface. So even if you have this rock eventually make its way up to the surface, the pseudotacholite very rarely survives. People have found examples of it though. I don't have any good pictures of it, which is sort of a roundabout way of saying that. But we know from laboratory experiments where people grind rocks past each other at really, really fast speeds that these do occur and do form, but that they also break down very quickly in the air. So they're rare to find, but they do happen. So any questions about this? Good to move on. All right. Moving along, hopefully. Maybe, there we go. So the next one is actually one of the largest categories of metamorphism. And we call it either regional or dynamothermal metamorphism. So dynamothermal, again, is a combination of dynamic, which is motion, and thermal, heat. And so the difference between that and just dynamic metamorphism is this is very quick and is just all about the movement. But dynamothermal has to do with continental plates slamming into each other. And so it's a slow motion. It's motion at the speed of plate tectonics, whereas an earthquake that would cause dynamic metamorphism is like miles per second. Earthquakes are crazy fast. But this is moving, plate tectonic speed. And so that movement of plates into each other leads to a bunch of things. It leads to high pressure because you're crashing two continental plates into each other. That's a lot of pressure. It also creates heat just from the collision, just because that's a lot of energy from things crashing into each other. And also, if you remember, both when we talked about continental plates and how they're thick, how when you do this, you have stuff that both bulges up and down. Again, like the squeezing food with force thing from last time. That also means that the parts that squish downward extend deeper down into the earth, into places where there's higher temperature. So even though the pressure is very high and is keeping it from melting, it's at very high temperatures, and so you can get some very strong metamorphism. So depending on where you are in a collision, you might get different grades of metamorphism. So like if you're at the edges, like if you're near the surface or near the top, you might get fairly low grade metamorphism because even though it's high pressure, the temperature's not that high. Then kind of once you start getting below the ground, you might start get intermediate grade. Sort of as you get further inward. But smack in the middle of one of these collisions, especially once you get deeper down, because it's high heat and high pressure, you're going to get high grade metamorphism. So you can kind of tell from what part of a continental collision that rock formed in or metamorphosed in based on its metamorphic grade. And so you might find low grade, intermediate grade, and high grade rocks just touching each other because that's just the way that they form. As you get deeper into the middle of the collision, the higher the grade. So does this make sense? Any questions about this, how this works before I move on to what you get in there? So yeah, the reason it says regional as well as dynamothermal is that this always happens on a very large scale. So something like burial metamorphism can happen in a small area. Dynamic metamorphism can happen in a small area. But this, I mean, you're slamming a continent into a continent. It's like the scale of the entire plate boundary. So the reason this is regional is just because it inherently affects a very large area. And as such, I will probably use that term more. I think your book uses them interchangeably. I like regional better just because dynamothermal is a little bit too much like dynamic. I just think it's clearer. But yeah, so the rocks you're going to get in there are they're foliated rocks, and they always involve neocrystallization. And so what specifically you get depends on the amount of pressure and heat, and also on what is in the protolith. But definitely the kind of foliation and the specific minerals that recrystallize, depend on the heat and pressure. So, so kind of going from lower to higher, from left to right. This is a place sort of in the edges or lower, like in the edges of a collision, you might start to get schist. And so in that case, you're going to have neocrystallization. Old minerals are going to break apart and form into different ones that you might see on that chart. And the foliation is that the minerals are going to align in kind of a fabric that has to do with the direction of compression. So in this case, can you see in this rock, are the bands aligned horizontally or vertically?
Horizontally?
Yeah, so they're horizontally. Kind of see here. So in this case, if they're horizontal, which way has to have this been squished? From the sides or from above and below?
From above and below.
Yeah, because that kind of flattens those layers like a pancake. So in this case, and that's actually true for all of these. So the same thing works for all foliation. But yeah, in schist, you don't get any reorganization based on mineral composition. It just forms that fabric. But then once you go up to higher grade, sort of closer to the middle of the continental collision, you get gneiss, which is high grade. And so in this case, you get an alignment in a fabric, but you also start to get things separating out into bands of mafic versus felsic minerals. The chemical bonds get broken enough that they find each other as quartz and they find each other as amphibole and so on and so on. And actually this would be, if you're talking about fascies, this is a green schist fascies, gneiss would be an amphibolite fascies. And so you get these layers divided up into bands of different minerals. And then as you go really into the bottom of the continental collision and that deep root of it that gets very, very close to the mantle, that's where you get the highest grade, which is called migmatite. And so in this case, the mineral also aligns and reorganizes into bands. So you can see this is similar looking to the gneiss, but look at this area, for example. I mean, and all of the areas that look like that. But does this look like anything else we've seen in this class? Not just in metamorphic rocks, but in the whole class.
Igneous?
Yeah, so doesn't it look a little like granite? Because you can see here, you've got your lighter crystals and your darker crystals, your pink, your gray, your white. Basically what happens in migmatite is it's warm enough that the felsic stuff melts, but the mafic stuff doesn't. And then when the felsic stuff hardens, you basically get, rather than this just banding of felsic and mafic minerals, you get bands of mafic minerals and bands of basically granite. And so you can tell this isn't an igneous rock because it's interspersed with the bands of mafic minerals. It's still a foliated metamorphic rock. In order for it to be igneous, the whole thing has to melt. Yeah, it's really cool. I think metamorphic rocks are, I think they're the most exciting to me just because some wacky stuff happens and they're cool looking. But yeah, so you basically get pockets of melt or layers of melt, and that turns into basically layers of igneous stuff, although it's part of a metamorphic rock. In order for it to count as igneous, the whole thing would have to melt, and then you would get something entirely different. So does this make sense? Any other questions about regional metamorphism? All right, let's move on. So another thing you can do, or another thing you can get, is called hydrothermal metamorphism. So we've talked a lot about how hot fluids influence things like sedimentation, like, you know, you can get sedimentary rocks from them. They can influence melting. They can influence a lot of things. But you can get mineral creation from hydrothermal fluids. And so in this case, hydrothermal metamorphism is when you have a hydrothermal fluid, a hot mineral-rich water, actually interacting with the surrounding rock, actually having a chemical reaction with it, both taking away minerals from the surrounding rock and adding its own minerals, basically forming new stuff where the hot water is interacting with the surrounding rock. And so this is most common at mid-ocean ridges because you have a lot of water in the ocean, which also has a lot of minerals in it because it's the ocean, interacting with lava coming out of the mid-ocean ridge. And so in that case, that hot water interacts with the rock around it and with the seawater, and then the seawater also sinks in to cracks around the mid-ocean ridge and heats up and also grabs minerals from the surrounding rock. And then those minerals are in there, which interact with the hot water, with the other minerals, and so on and so on and so on. Kind of like a feedback loop of things coming in and out of the ocean and the rock and the volcano. And so you can get some really wild stuff in there. So the heat flow in these varies. Sometimes it can be really hot if the mid-ocean ridge is actively erupting. Sometimes it's moderately hot. It also depends on how far away things are. So it'll be more extreme closer, less extreme further away. This can also happen near other volcanoes on land. This isn't only in mid-ocean ridges, but you do need to have water involved. So if you have a volcano on land and no water nearby, it's not going to happen. But like in places like, say, Yellowstone, where there's geysers, you absolutely get a lot of this. But yeah, this is a high heat, low pressure thing. And so the grade, because it's happening on the surface or very close to the surface. And so the grade of metamorphism varies depending on the heat. So any questions about how this works? Hot water, full of minerals, chemical reaction with the rock. And so actually, rather than this forming specific kinds of rock, more often this forms like bands or veins or loads of things in other rocks. So this is actually really responsible for a lot of major mineral deposits, since rather than necessarily dissolving or interacting with the entire rock, the hydrothermal fluid is going to get into the cracks and weaknesses in the other rock, and kind of that's where it's going to have the easiest time doing a chemical reaction. Just like when we talked about chemical weathering, it was a lot easier for those chemical reactions to occur along breaks and surfaces than through the entire rock. And so in this case, like on the left, these are veins of probably calcium-rich minerals that have occurred in this other rock. I think this might be basalt. It looks like basalt. But you just, and that would make sense for a mid-ocean ridge, of just these veins of new minerals forming from chemical reactions, because basalt sure as heck doesn't have calcium in it, but other things in the ocean might, and therefore might cause this interaction and cause these veins of minerals, and these are called veins, by the way, to form in cracks in the rock. But this same kind of behavior is also how you can get things like gold or silver. Pretty much any major mineral deposit, anything that's led to mining and bonanzas and things like that, come from hydrothermal metamorphism within existing rock, exploiting cracks in the rock and interact and pulling molecules of, say, gold atoms out of the surrounding rock and then pooling them together into veins, or the mother lode, actually LODE, refers to a very big vein of gold. And actually California's gold rush is a result of hydrothermal metamorphism. Well, because there used to be a subduction zone in California. And so when the Sierra Nevada were forming and when certain rocks were forming there, this process was occurring and causing gold to pool up in cracks in the rock. And then over time, that rock lifted up and exposed itself to the 49ers, the miners, not the football team. Any questions about this? I mean, the football team is named after the miners who showed up in 1849. But any questions about how this works? All right. So yeah, chemical reactions, not exciting enough for you. Let's get hit with a space rock now. So shock metamorphism is probably the most dramatic because it really is extremely instantaneous and especially bad news if you are a dinosaur. So basically shock metamorphism pretty much only occurs when a space rock hits the Earth. So this is the least common because luckily for life, that doesn't happen very often. But basically, as you might expect, a giant space rock punching the planet is going to produce a very strong amount of pressure and also a lot of heat because that thing is coming through the atmosphere and getting heated up from friction with the atmosphere. And so when it hits the ground, first of all, it's already hot. And then also just impacts produce heat, collisions produce heat. But then also it's going so fast that it makes a massive shock wave that ripples out through the surrounding rock. So shock metamorphism works in a couple of ways. Some of it is just that the stuff directly at the impact site does melt. It melts, but not in an igneous way. It melts kind of more like in the dynamic metamorphism, where it's around the site of the impact, but not pervasively everything. But more significantly, this sends a massive shock wave rippling through the Earth. Kind of like if you were to drop a rock into the water, it would produce ripples around that. This is a space rock producing ripples through the Earth rock. And that is an extremely high pressure situation. And the pressure of that wave propagating through the Earth is enough to actually change the surrounding rocks. So it's not just the heat of the direct collision, but the pressure from that wave rippling out through the rest of the Earth. It's really, really dramatic and very instantaneous. So this is kind of an unusual case. You get very high heat at the impact site, low elsewhere. The pressure is insanely high everywhere. And so the grade of metamorphism you're going to get is moderate to high, depending on how close that you are to the impact site. Dinosaurs are bemoaning being close to the impact site. But yeah, this is just unsurprisingly, shooting a space rock at the planet is going to cause some stuff. So are any questions about how this works? So even though this isn't very common, we know that it's happened because you can find craters on Earth. The crater that we now know is related to the extinction of the dinosaurs, kind of offshore of the Yucatan Peninsula in Mexico. So that's underwater. But things like Meteor Crater, Arizona, there are places where we see craters and we see these rocks. And it leads to some pretty wild looking stuff. So rather than necessarily forming specific types of rocks, it kind of leaves features. So on the left, this is I think this is just the hornfels, but do you see these kind of triangular features that are all radiating from one side of the rock to the other? Do you see these? So those are called shatter cones. And basically they are caused by the shock wave propagating outward. And so in this case, like if you can imagine, just imagine, imagine, throwing something hard into a bunch of loose sand, and it would scatter out into a pattern like this. And so basically what this is saying is that the impact was over here somewhere. And then the shock waves rippled out this way. And as it did, those shock waves rippling out produced these triangular features in this rock. And so if you see something like this, and especially like you also see like these littler kind of splash zone looking features. So that is a result of the shock wave blasting these things out of the way, which I think is pretty wild. So this is very uncommon, but it does exist. And the heat from impacts can also form pseudotacholites, but in a very different way from in a dynamic metamorphism. So in a dynamic setting, you're really only going to get it on the surface of the sliding area. But in shock metamorphism, you're going to get it in the whole dang impact crater. And so in this case, all of the black stuff is pseudotacholite. All of the black stuff is stuff that melted related to the heat of the impact and then immediately recrystallized, reformed into metamorphic glass. And so in this case, it kind of looks like a conglomerate, but it's all metamorphic because rather than this being cement, it's glass. And so this stuff, basically this other stuff was just not able to melt at the temperatures of the impact. And so the stuff that did melt recrystallized, and the stuff, or neocrystallized, I guess it's mostly recrystallization, and the stuff that didn't melt is just there. And so even though felsic stuff melts at lower temperatures, this is black just because it also includes all of the ash and crazy stuff and ejecta and stuff getting blasted in the air and then dropping back down into it and making it look dirty. There definitely is smoke and stuff involved too. So in that case, the black stuff melted and the other stuff didn't. This probably was a sedimentary rock before, but it's hard to say. But any questions about this? Pretty wild stuff. These are some of the most uncommon rocks on Earth. Again, just because luckily we don't get hit by space rocks very often. But moving on to stuff that is very common, the last one we're going to talk about is subduction zones. And we've talked a whole lot about subduction zones in other contexts of this class. We talked about it just with plate tectonics, where if you have an oceanic plate shoving under either another oceanic plate or a continental plate. And we've talked about them in the context of volcanoes because the subduction process brings that cold water down, which allows this to melt. But in the context of metamorphic rocks, the area where most of the action is actually before you get down into the melt zone. And so in this case, you have very high pressure, as I said, because things are crashing into each other, but very low temperature because this drags ocean water down. And so as such, you have this situation where you get into that blue schist facies of, again, high pressure, low temperature. And so you can set some rocks here, they're literally just high pressure, low temperature rocks that just come from that squeezing under those temperature conditions. But you can also get some where the ocean water actually gets involved in a chemical reaction as well. Especially shallower, like in here, in what we call the accretionary prism, where again, a bunch of stuff weathering off the continent, eroding off the continent, a bunch of stuff pouring down in the ocean goes into the ridge between the trench between the plates and just kind of builds up. And so there's a lot of room in here for water to have chemical reactions with this stuff as well. So you kind of get two categories, either ones that do involve the chemical reaction with the water and ones that don't. But no matter what, it's high pressure. And we call them both blue schist facies. So does that make sense? Yeah. And these are also some of the most common metamorphic rocks, just because there are so many subduction zones on Earth. But there are the main kinds of rocks that you get in these are colorful. So subduction zone rocks are really cool. They actually, for the most part, all start as basalt and then change, and basically whether they turn into blue schist or serpentinite depends on whether or not you add water. So blue schist, which is the fascies name, is really blue, like it's blue. This is a particularly bright blue one. Some of them are more of a bluish gray, but they can be like straight up blue. And this starts as basalt and just changes its mineral content due to the pressure and temperature, the high pressure and low temperature. But serpentinite, which is so named because it looks kind of like a snake, is also starts as basalt, but in this case, the ocean water has chemical reactions under that high pressure, low temperature situation. And water actually works its way into the chemical structure of the rock, turning it into serpentinite. And so this particular example is kind of a grayish green. You can have some that are blackish green. You can have some that are lime green. These come in all kinds of colors, but they're just from that subduction zone, chemical reaction, low heat, high pressure. And serpentinite is actually California's official state rock. So there's a lot of this. We used to have a subduction zone and now we don't. And so a lot of this stuff ended up on land in really scenic places. There's serpentinite right under the Golden Gate Bridge. Like half of the Golden Gate Bridge is anchored in serpentinite. My background picture is in the East Bay near Oakland, and there's a serpentinite outcrop. And our state flower, the California poppy, really likes to grow in serpentinite. So a lot of our sort of state icons are affiliated with that. And so it's just a pretty iconic rock. Like if you've never sort of been to the Bay Area, there's places where you can go that have green soil because there's so much serpentinite. So it's really common here. And a lot of our other state things like redwoods like it, poppies like it. So this is our state rock, and it's a really cool rock because it speaks not only to just metamorphism being interesting, but also to the geologic history of California, of how we changed from having a subduction zone to having the San Andreas Fault, which is not a subduction zone, and which we'll talk more about the week after Thanksgiving. So any questions about either of those? Yeah, I think it's super cool. I love serpentinite. Like I have a bunch of it. Like I collect some whenever I find it. I have a bunch of it just in my apartment. So how they get the color, it has to do with certain minerals that form under those conditions. So blue schists, it's mostly a mineral called glaucophane. You don't need to know that. And serpentinite come from serpentine minerals that just happen to be what happens when you introduce water to basalt. But yeah, they're really, really colorful. So real quick, I just want to end, but then with two more quick things. But then if you have more questions or want to talk about more stuff, feel free to hang out. But yeah, how does this stuff get on the surface? Like all this happens pretty deep down. How do we find it? Like if it requires high heat and pressure, which generally don't happen on the surface, how do we get it? And there's two major things, like how do we know it exists here as geologists on the surface? And so one thing is just accretion. So back to our subduction zone. This glob of stuff, as plates are shoving together, is ultimately going to get shoved this way and then get stuck onto the continent. And so that's actually how all of these metamorphic rocks, like the serpentinites in California, ended up stuck onto the continent, is because this got shoved onto land as subduction stopped and turned into the San Andreas Fault, and then just got stuck. So that's one way. But another way, which leads into what we're going to talk about next class, is called exhumation. So basically, when you form mountains, when you crash two continents into together, you form mountains. They're tall. But once that continental boundary stops, once that continental collision stops, eventually those mountains are going to erode. But when they erode, it's as that erosional process happens, basically the stuff that gets exposed is going to be the stuff from all parts of the collision zone. So you might see low-grade stuff, middle-grade stuff, high-grade stuff as that surface erodes to flat. So that's one of the best ways. Just erosion is what exposes a lot of the most extreme metamorphic rocks. And with that, that's all I have for today. I hope, are there any questions about either erosion and exhumation? or about accretion? If you don't have any, don't worry about it. The quick quiz will be up right after class. The next vocab for Monday's discussion will be up after class. I'll post the slides as soon as they upload. The practice problems for the metamorphic grade stuff will be up really soon. I kind of wanted to wait on those to see how things went today. But yeah, that's it for now. If you have any questions, feel free to hang out and ask. If you have a question that's not about geology, yeah, feel free to hang out. If you don't have a question, I will talk to you all later. But yeah, go for it, Elaine. Yeah, and have a good, what's my Hogwarts house? Ravenclaw. Really? What would you have guessed? I'm curious. Hufflepuff. That's actually, I've taken the sorting hat test more than once, and one time it said Ravenclaw on one side, one time it said Hufflepuff, and I was like, yeah, I can see both of those. But I kind of tend to say Ravenclaw more because I was always that kid who would like stay up later than I was supposed to reading about things. And nice, you're literally wearing a Hufflepuff sweater. Nice. I was always that kid who would kind of I was the insufferable know-it-all kid. And now I'm a professor, so I guess it pans out. But yeah, yeah, I feel like Hufflepuff is the most underappreciated house. Also, I have to tell one of my other friends about one of this. Yeah, I stuck to doing what I love, which is the best thing you can do. Like if you can, find a job doing what you love, it's awesome. I definitely feel very lucky, but it's also like the more of a strong idea you have of what you want to do, like if you know you love this thing, then like it kind of pans out because you feel more and more driven to keep doing it. And the more driven you are, the better you'll be. And the better you are, the more likely you are to get a job in it. So it kind of all pans out. Like finding that thing is awesome. But yeah, I'm definitely gonna have to tell one of my other professor friends about this conversation because her class was arguing over whether she was a Gryffindor or a Slytherin. So I think she'll find this very amusing. I would definitely call her a Gryffindor, but yeah. But, anyone have any other questions, thoughts? Have a good one. Yeah, have a nice Thanksgiving. Well, I will see you all on Monday. We do have class on Monday, just not Wednesday. See ya. Mario, are you hanging out with a question, or are you just taking notes, or are you just zoned out? Oh, yeah, you're there. Okay, cool. I will talk to you later. Have a good weekend. Well, let me end the slideshow in pencil mode. Maybe it won't. Come on. There we go.